It's a live Q&A from Astrocampus's 10th birthday party.
Oh, there's a really bright light on that robot.
Robots with really bright lights. That can only mean one thing. Dear. Emily, we're not sitting around the table in your office as we normally would. We're in a very crowded place somewhere else. What's going on? What is happening here?
We're in the middle of a space exhibition.
We are. Where are? We're in the exhibition centre at the University of York, appropriately named. But why? Why are we here today? What's going on?
So we are here to celebrate the 10th anniversary, 10th birthday even, of the Astrocampus.
Very exciting. And Astrocampus is something which is very, very close to your heart.
Yes. Well, I've been the director of Astrocampus since it opened, which was...
Since the beginning.
March 2014.
Yeah. Very exciting. So 10 years.
10 years.
Can you believe it? They grow up so fast.
Oh, yeah.
There'd been a few changes, I'm guessing, since it started?
Yeah. I mean, for me, for the Astrocampus, for the university, it's space. I mean, it's an amazing thing.
Very, very cool. But the whole point of what we're doing here today is so that we can do a little bit of space Q&A. So we can come back and talk a little bit more about Astrocampus in a minute. But I've got some very excited space fans sitting here in front of us who have some questions for us. Do you know what your questions are? Have you got a question for Emily? Yes. Okay. Well, hang on. Who wants to go first? All right. Then what I'm going to get you to do is to speak into the microphone like I am, but I'll turn it around to face you. Just get down nice and close, ask your question, and then Emily can answer.
My name's Rowan Mitchell, and my question is, what would the universe be like if there weren't any black holes?
What would the universe be like, Emily?
It's a meaty one to start with.
That's a really good question.
It's a really good question. So I was thinking about what the universe would be like in terms of the whole mass of the universe. So if you actually add up all the mass that's in black holes, it turns out to be something like 0.01% of all the normal mass in the universe.
So for people who don't do percents in a big way, that's like not a lot, right? That's a tiny amount.
That's a tiny amount. And that's even of the normal mass. So that's not including all the wonderful dark matter, that's not including dark energy, that's just like the stuff that we can see, touch, eat, drink, whatever, right?
Yeah.
So,
don't eat black holes, kids, that's a bad idea.
In that sense, black holes are not that big a contributor to the makeup of the universe. However, that is going to change, right, as time goes forward. So let's fast forward the universe. More and more black holes will form as stars end their lives. So there'll be more and more black holes in the universe. And eventually, maybe it will just be mostly black holes in the universe.
So in the far, far future, it's all black holes.
Potentially.
So if you take away the possibility that there's no black holes, you can't have black holes at all anymore, then what would happen?
Well, that's interesting, because black holes tend to lock matter up, right? So black holes are formed when the very, very large star comes to the end of its life and it self-collapses in on itself to this black hole. And then it locks up that matter, right? That matter's kind of, it's done. It's in that black hole. You can't get out, so it's there forever, as far as we know.
As far as we know, yeah.
So what would happen if that matter didn't go into a black hole and just returned back into space? Well, then that matter could be available to the next generation of stars. So that matter could go into the next star, maybe like the sun, the next planet that's going around that star, something like that. So although the fraction of matter that's in these things is very, very small, over time you could imagine there's much more recycling of material in and out of stars.
You could recycle the stuff more. Maybe you'd get a few more cycles of stars and planets and stuff, but instead it all gets locked up in black holes and put away in a corner saying, don't go here, don't look at that, that's not available anymore.
Yeah.
Right. So that could make a huge difference in the future for numbers of cycles of stars. Yeah. Maybe.
So that's kind of, that was I was thinking more about what we call stellar mass black holes. So those are the black holes
Those
formed,
are the little ones.
Yeah. Well, they're still the size of stars.
Little, yeah.
So, yeah. Comparatively little. So they're the ones that form at the end of the lives of big stars. But we do have, of course, these supermassive black holes.
Right. Now, have you heard of a supermassive black hole? Yeah. You've listened to our podcast before. We've talked about supermassive black holes, right? So big things.
Yeah. So these are the things that are centers of galaxies, right? We're talking something like 1 billion times the mass of the sun. massive things.
That's crazy.
Enormous things.
That's
yeah.
ridiculous.
And these are the things that fuel, we've talked about active galactic nuclei or really massive, powerful feeding black holes that are pumping out energy into the universe. They're just insane objects. So to not have those, I think, is actually potentially more impactful.
So what does that do? I mean, do we need those?
Well, our galaxy is kind of built around the supermassive black hole.
Yeah.
There's an open question as to which came first, the black hole or the galaxy, right?
Right.
So maybe,
so if you take away the possibility of those existing, maybe we just don't even have galaxies.
yeah, or galaxies might look very different. They might be a lot smaller because they don't have this big central mass to hold everything in by the gravitational pull.
That'd suck. That'd be
Well-
it'd be just completely different.
It would be
the
really
whole
different,
Milky
yeah.
Way would just be just a wash. It would
Yeah.
be just wouldn't.
It would
cool.
be really different. So examples of galaxies that don't have black holes or satellite galaxies.
Right, because those exist.
Yeah, yes.
Yeah.
Or even things like the Large and Small Magellanic Clouds, right? They're clusters of stars that sort of orbit around our galaxy, but they don't have a black hole. So maybe all galaxies go to being things like that.
Cool. That was a much deeper question than I thought. That was awesome. Thank you
Yeah.
so much. You've kicked us off with a really, really good question. Would you like to ask us your question? Okay, so hang on. Let me set up the microphone.
Hello, I'm Finn Mitchell, and my question is, how close to a black hole would an object need to be affected by its gravitational pull?
Another black hole question. How close would an object have to be to a black hole to actually feel its black holeness? Its black
Yeah.
hole locality, I think, is the actual term. I think that's the scientific term, isn't it? Black hole locality?
Yeah.
Yeah.
So this is a great question as well. So there's a technical question, but there's also a really nice, I think, side thing to talk about here as well.
Okay,
So
all
let's
right.
go for the technical part first, right? So the way that gravity works is that everything with mass is then acting with this force of gravity. So you have two masses, even between yourself and me, you and the table, everything's got gravity, right? Acting between it.
You and Emily are orbiting around each other right now as we speak because of gravity. Yeah, really, really slowly, but yeah.
Exactly. So gravity exists between any two masses anywhere in the universe. The question is distance and how much mass there is. So if you have a big mass, you have a big influence because you're going to influence further things that are further away. If you've got a small mass, much less influence, right? So I don't have much mass compared to the Earth, so I don't really influence a lot of gravitational force on the Earth. That's sad. Mostly the Earth influences it on me and causes me to fall downstairs.
Yeah.
That's how it works. But that's distance dependent, right? So every time you take a step further in distance, it actually drops by a square. So if you were 1 meter away from an object and felt the force of gravity, if you go 2 meters away, that force goes down to 1/2 squared. So 1/4, 1/4.
So it drops off pretty quickly,
And
is
then
what
it goes,
you're saying.
every time you're going off the 1/over distance squared. So that means it drops off really quickly. If you were to draw a graph, it'd go downwards
Right.
in this really steep curve. Same is true for black holes. It's just that black holes have a lot of mass, so therefore they do influence quite a reasonable area around them. What I think is a really nice ancillary question, and maybe it's the root of your question, is kind of how close could you get to a black hole and not be eaten up, basically. That's a really good question.
That's the interesting part about black holes, right? Is the being eaten up part, right? It's being pulled apart by one.
The
Because just to be
spaghettification,
clear,
right?
like the sun, you could replace the sun by a black hole right now, and other than the fact that we wouldn't get any light from it because it's black, we would keep going around it. Like the gravity would still be there. We just keep going. That wouldn't make any difference. But I think you're right. You're after is, but when's it gonna pull you apart? That's the fun part.
Yeah.
Right.
So there's this wonderful point of no return for a black hole called the event horizon. If you're inside the event horizon, it's all over. You're done, right? You're in the black hole. That's it. There's nothing you can
No
do.
coming out.
And that event horizon is set by the fact that we've got the speed of light, and nothing can go faster than the speed of light. You'd have to go faster than the speed of light if you were closer to a black hole than the event horizon, and you just can't do it.
Einstein said that's wrong. You can't do it. Not allowed.
So
Against the rules.
it's not going to happen. So you can ask where that event horizon is, and it's different for different black holes. Big black holes have larger event horizons, and smaller black holes have smaller ones. I think it's quite interesting to look at, say, the black hole in the center of our galaxy. So if you're going to look at that one, I think the numbers work out that if you were able to travel just about the speed of light, not quite, but just about, then you'd be looking at a few thousands of kilometers away. It'd be the closest distance, which is
On an
shockingly
astronomical,
close, actually.
that's actually quite close. It's not very far
Yeah,
away.
like
yeah.
a few thousand kilometers. That's kind of like the size of Earth, right? Diameter of Earth, something like that. Whereas if you're talking about a black hole that's the mass of the sun, so all the sun's mass in one single black hole, I think it's only about 1 or 2 kilometers. So you can get really close to these things
Yeah.
if you can travel really fast.
Yeah. But the
Yeah.
other cool thing is that the closer you get, the bigger the gravitational pull is on one part of your body compared to the other. And that's when spaghettification happens, which is the coolest term, actual astronomical cosmological term in the history of all cosmological terms, which is stretching you out into spaghetti.
Yeah, we did good with that word.
Yeah,
Yeah.
which I think is awesome.
Yeah. Basically, the gravitational force, let's say you're heading towards a black hole feet first, because that's always the best way to spaghettify yourself, right? Feet first. It means that the force on your toes is much, much bigger than the force on your head. So if you've got more force on your toes than you do on your head, you're going to just stretch out into this lovely long line.
Now, on that, we've had an extra bonus question here from Dad, I'm guessing. Yeah. Which has been written down on one of our Syzygy postcards, which is, but would you know that you were being pulled apart because of things like time dilation effects? Because this is getting really intense here, right? But the stronger the gravity is, the more the space-time is being warped and bent and weird stuff happens, like time goes all crazy. Time moves at a different rate to when you're further away. And so would you even know? My guess is yes, but I haven't looked into it. I need to ask someone who's a cosmologist, unless you know the answer.
I'm going to go with actually it's probably no. Because the time dilation means that for a second of time that's passing for you being close to the black hole, a lot of time is passing to someone observing you from far away who's not in that gravitational field, right? So the person who's seeing you get spaghettified sees it happen relatively quickly, but you might only experience it really slowly.
Well, that's true. I mean, it doesn't. Don't they say that it takes you an infinite amount of time to actually pass over the event horizon into the black hole because of the... This is hard stuff.
Yeah.
I need to go and find someone who knows. We need a cosmologist. That's it. We need another chair with a cosmologist. Excellent questions, though, guys.
Brilliant questions.
Really good questions. And even more questions coming. If anyone passing by the way, wants to join in, if anyone's got a question for astronomer Emily, that's what we're doing today. We're doing live Q&A for the Syzygy podcast. So, yeah, that's where we're at. Emily, we're off to a very, very good start.
Oh, yeah.
I think we've got another question from one of our visitors here. So, you got your question? You ready to go?
I'm Henry, and I would like to ask a question. Do you know if this galaxy or the Andromeda galaxy will ever be destroyed by a quasar?
Will this galaxy or Andromeda, we're giving the option, ever be destroyed by a quasar? So that tells me, first of all, A, I mean, you know that we're in a galaxy. B, you know there's another galaxy called Andromeda, which is really cool. And C, you know about quasars? Emily, what's a quasar?
Oh, wow.
Let's start with
quasars.
that.
Yeah, so quasar stands for something called quasi-stellar object. It's actually nothing to do with stars.
Right,
surprisingly.
okay.
So quasars are really, really distant, very, very energetic centers of galaxies that we can see. They are some of the most energetic things in the universe. So I can see where the question is coming from, because you might think, therefore, they can they shoot these kind of very powerful beams of radiation, which are kind of like the universe's mega laser guns.
They're like an enormous Death Star.
Yeah.
Like, they're just nuts, these things. But they're huge, right?
They're huge. So,
absolutely enormous.
So they are actually feeding black holes. So coming back to black holes, right?
Another black hole question,
So these
really.
are very, very big supermassive black holes in the centers of galaxies that are feeding, and during that feeding process, the material is going into the black hole, and they're sending out all this energy at the same time.
Okay, so the question then of, could our galaxy or Andromeda, one of the two, your choice, could that be destroyed by a quasar? So first part, does the Milky Way or Andromeda have a quasar?
No, we don't.
We
No,
don't.
We don't have.
Okay,
we don't
so
have,
there's number one.
Yep.
Yeah.
So we just got normal garden variety black holes that are not feeding at the moment.
Right,
So
okay. But could they feed? Could they turn into quasars?
That's an interesting question. Maybe. But there might have to be some kind of big bit of mass going to the center of the galaxy. There's got to be something to eat, some food, right?
Right.
So we need a whole lot of mass. And at the moment, neither of those galaxies have that.
Okay. But let's say it did, right? Let's say something did happen. Like, have you heard that our galaxy and Andromeda are going to collide at some point? So what if, when that collision happens, you end up with a whole bunch of mass around one of those supermassive black holes and it does start feeding? Then, getting to the heart of the question, what would that do to the galaxy?
Yeah, it would certainly turn into one of these really very high energy feeding black holes. We might not call it a quasar just because quasars we talk about as being from the very early part of the universe, right? So right when the universe was born.
That's a particular thing.
Things that are like that but happen today, we tend to call active galactic nuclei, or AGN.
Right.
So, and I guess the answer to the question is the Andromeda Galaxy and the Milky Way Galaxy are probably going to destroy each other and merge into one giant galaxy.
Called?
Milkdromeda.
Milkdromeda. I mean, can I just say, sorry, that's a really dumb name for a galaxy. Like, you take two galaxies and merge them together to make super huge galaxy. What are we going to call it? Milkdromeda? Really? Brilliant, you think? Okay, I'm overruled here.
Yeah.
But, so that would destroy those two galaxies. We'll actually merge them.
Yeah.
But if one of those AGN, the active galactic nuclei, let's call it a quasar, were to turn on, like, would that destroy the galaxy, or is that just a really cool feature of this new Milkdromeda that we would have?
Well, you wouldn't want to go anywhere near it, put it that way.
Okay, fair
right?
enough.
It wouldn't be a nice place to visit. But probably the merged galaxy Milkdromeda would survive. It just wouldn't be a very nice place to live in.
Right. Okay, so I think the answer to your question is no, but it would still be really cool. So, something to look forward to in the far distant future.
Question.
Excellent question. Thank you very much. Enjoy the rest of the show. See you later. Dearie me. Emily, we're off and running with a bunch of black hole questions. It doesn't really surprise me. I mean,
No.
I think if you were to ask a bunch of people out there on the street, do you have a question about space? Most people would probably say no. But people coming to this thing, right, this very special exhibition of Astrocampus-related, space-related, science-related stuff, is going to attract a very particular kind of person. And we've already seen, just from the questions so far from these kids, they're switched on. Like, that kid who just asked that question, like, I don't know how old he is, but he's not old. And he's asking about quasars?
I didn't learn what a quasar was until I was at university.
That's nuts. So listen, tell me a little bit more about Astrocampus. 10 years old. What goes on at Astrocampus? What's the big deal?
Let's rewind. Yeah, what even is an astrocampus?
Yeah.
Because we throw that word around,
We
don't
did,
we? But
yeah.
we take it for granted.
Like
that
everyone
people know
knows.
what it
Everyone's got one.
is. Yeah.
Everyone should have one.
Well, indeed. So the Astrocampus was this purpose-built observatory at the University of York. It was actually the genesis of a lot of really passionate people in the Department of Physics at that time who wanted to set up an observatory that had sort of some really key features. First of all, it had to have some really awesome telescopes for students to
The
use.
telescopes make the observatory, right?
Yeah,
I mean, that's the whole
absolutely.
point.
So we had got to get some good telescopes so that students studying astrophysics had some really cool equipment that they could train on, learn on, etc. But there was also, we wanted to keep it on campus so that it would be easy to get to. Because often you put observatories that are associated with universities, you might put them far away.
On a mountaintop somewhere.
Well, that
Turns
would
out, not a lot of mountains in Yorkshire.
Well, no, that's true. And also, even if you do move it to, say, a darker site, even a site with better weather, it becomes difficult to get to and from. Right?
Yeah.
It becomes a bit less
Yeah.
accessible.
Yeah.
So, wanted to keep it on campus.
Yeah.
And
well,
then,
just being able to stroll across the, 200 metres from the physics building to Astrocampus, like there's no barrier there at all for entry.
No.
You just go do it.
Exactly. And it means we can look after it easier, we can have technicians on site, all that sort of thing. It's really, really useful.
Yeah.
And then, of course, we wanted to have a site that would be engaging for the community, right?
Right, yes.
So
teaching and outreach.
Yeah, bring people to the university, bring people to the observatory, look through telescopes, talk about space, talk about science, as we always want to do, inspire the next generation of people who are going to ask all these really hard questions about black holes and probably go away and answer them one day.
Because black holes are your specialty. We know that. We know that, Emily. So what sort of stuff have you got over there? Well, I mean, it's all about the telescopes. It's all about the gear. It's all about the kit. So what special kit have you got at Astrocampus?
Well, there's been an observatory there for a very, very long time. I think
Right.
in the 1960s it was open, not long after the founding of the university itself.
Okay, so Astrocampus was sort of built around the observatory.
Well, yeah, so it wasn't the Astrocampus at that point. It was just a single brick building with a dome on it that
Gotcha.
you stick a telescope in.
Gotcha.
Away you go. So that telescope's been there for a while. But there's always a little bit of a trade-off. Having a telescope in the UK, you know that it's not going to be the best site in the entire world, right?
Listen, listeners, if you're not from the UK, all of the stereotypes are true. There's a lot of cloud cover.
Yeah.
Yeah.
And it rains.
Yeah, a lot.
Yeah.
A lot.
But that's fine. And we do get enough clear nights over the course of the year to get a few really good observing sessions in. And that's all you need to do the teaching that we're doing, and obviously just even getting kids in to look at telescopes.
Yes.
They're thrilled by it,
Yeah.
right?
Yeah,
That's cool. So, but we wanted to broaden out and do some other types of astronomy that you can do when it's cloudy, that you can do even when it's raining, and you can even do in the daytime.
Wow. Does such astronomy exist,
Oh,
Emily?
of
What
course
kind of
it
stuff
does.
do you do?
So we also do a lot of radio astronomy,
I see.
looking at radio waves.
So you got radio telescopes out there. You got
Yeah, we've
radio
got a few,
dishes.
Yeah, so those are really useful because we can work around the clock on those. We can work any type of weather. It's really, really good.
That's awesome. So you got the dome, which has got the optical telescope in it. But then tell me about the radio telescopes. What have you got out there?
Yeah, so they're big dishes. So radio light is a much longer wavelength than optical light, which means we need bigger telescopes to collect it, right?
Yeah.
So once our optical telescope, the biggest one we have is 16 inches. That
Yeah.
means the mirror is 16 inches in diameter.
Which is not small.
No, it's very sizable, actually. So you can get some nice stuff with it. But when we talk about the radio telescopes, we've got dishes that are 3 meters in diameter. So these big dishes. And we've even got some radio telescope that look a little bit just like antenna.
Yeah, when I first went over there, I thought they were like, I don't know, just flagpoles or something. It took me a little while to recognize, like, oh no, that's actually part of the gear.
Yeah.
These are not dishes at all. They're just big poles with wires going between them.
So those are called half-wave dipoles.
Right.
And they're the kind of instrument, actually, if you are interested in pulsars, they're the kind of instrument that Jocelyn Bell Burnell used to detect pulsars on.
Okay.
And what they are, they're just a wire. They are just a wire strung between 2 poles up in the air. But when you get the electromagnetic signal from a radio wave, it resonates on that wire and you can detect different signals.
Very cool. So students who are studying physics with astrophysics here at York, as part of their degree, they can just wander a couple of 100 meters down the road here on campus, and they've got pretty sizable optical telescopes. They've got radio dishes. They've got these radio dipole antennas. Like, this is real stuff, right?
Yeah, absolutely.
Yeah. That's awesome. Do you have... We've just been approached by a young man who has a look in his eye that says, I've got a question. You got a question? You want to ask Emily? Okay, so what I'm going to do, I'll turn the microphone around.
My name is Alexis, and my question is, do you think there's life outside of the solar system?
Oh, that's a brilliant question. I love
Really
this
good question. And can I just tell you, it's not a black hole question.
No.
We've had all black hole questions so far. So, Emily, do you think there is life outside of the solar system? So you're actually jumping, like, forget about the moon, forget about Mars, forget about the moons of Jupiter. Outside the solar system, in the galaxy, in the universe at large, is there life?
Oh.
What do you think?
So, I'm going to tell you a couple of things. First of all, you know that there's lots of planets going around lots of stars in our galaxy, going around lots of stars in other galaxies.
Well, we've got 8, right? We've got 8 planets around just our one
Yeah, we're kind of greedy,
sun.
though.
But how many, like, on average, how many planets do we think each star would have?
So we reckon there's about 300 billion stars in our galaxy.
Just in the Milky Way, 300 billion stars. And how many planets per galaxy?
On average, there's 1 planet per star.
So, okay, 300 billion planets.
Yeah,
All right.
That's a lot of planets.
And how many of them have got giraffes?
That's a very different question.
Yeah, okay.
So I'll get to the point. I think personally, my own opinion is that probably not.
Ooh.
And that's interesting. Well, I'll tell you why. because I think that astronomically, the likelihood of there being another planet out there that's very similar to the Earth is probably very high. We just talked about there's 300 billion planets.
Like some of them
in
have
the
got to be
galaxy.
like us, surely.
And there's hundreds of billions of galaxies. There's got to be other planet Earths. But this is where I'm showing you what I don't know. I don't know the biology very well, but from talking to other people, the chances of the biology happening, that life starting, seem to be so extremely rare that to me it seems almost like it seems really difficult to imagine. Even if you found 100, 1,000 other Earths, would the biology be the same? Would the conditions for life be the same? I don't know. I think maybe not.
See,
maybe that's even.
I find that so interesting because we're looking at the same numbers, right? And Emily is saying, "Nah, I don't think so." And I'm going, "Oh, come on! What are the chances of this place being the only place that can have us and microphones and podcasts and, you know, inflatable planetariums and frogs and giraffes? Like, that's just ridiculous." So I'm going to turn it around. What do you think?
I think that because there is an Earth, I think there probably is another planet where there is life outside this galaxy. I think there probably is.
You heard it here first.
And
I've got a challenge
your
for
guess is
you.
as good as mine at this point.
I've got a challenge for you. I think you need to be the one that goes out and finds out, right? And so you've got to go and become an astrobiologist, I think is the term.
Yeah.
And go and find it. And then let us know. That would be awesome. Thank you very much for your question. That was great. And it
Awesome
wasn't a black
question.
hole question, which is even better.
Yeah.
Awesome. Thanks, guys.
See you guys.
Ah, dearie me. Yeah, I don't know. It's such a difficult question because it really is one of those, who knows?
Well,
Like,
exactly.
we literally have no idea.
It's one of the things you can legitimately just have an opinion on.
Yeah,
right?
exactly. But I
Because-
do find it fascinating that we look at the same data and just fall different ways off
Yeah.
that line. To me, it's just unfathomable that there isn't. Like, I don't think there's necessarily giraffes, but there's got to be, just like, if we're here, there's got to be something.
Yeah, but how chancy was that, who knows, lightning strike
I don't know.
into that glob of green time? Maybe it's just the unknown, right?
Yeah.
Maybe
Yeah.
because I don't understand the biology as deeply as I do the astronomy.
Yeah. Yeah.
I'm just willing to give it the benefit of the doubt.
Do you know what would be really weird? Like, there's extremes here, and one extreme is we're the only one because it's so rare, and there's what do they call it, the anthropic principle, where we're here to ask the question, but the only people who could ask the question are the ones who are here, and so we just happen to be here, but we might be the only one. And that's one end of the spectrum. The other end of the spectrum is it's everywhere.
Oh,
And we just
yeah.
don't see it, mainly because, evolved life at a stage where we would understand what communication with them means, the chances of that overlapping with us is also incredibly small. But life could be out there, like, all over the place. What would be really odd, though, is if it was somewhere in between. If it was like, in the entire universe, the observable universe, what if there were like 3? Like 3 planets where it happened, and
that's much harder
there's
to
nowhere that
understand,
you could
yeah.
ever find them, and they are out there. But there's just 3. I was like, oh, I don't know what that means. What's going on? What does that even mean? I don't know. That's very odd.
But that's a question of our time. I mean, if you ask the same question of humanity in 1,000, a million years, is the answer still the same?
I mean, yeah. What is going to be here in 1,000 a million years? What's going to be here in 10 years, Emily? I think let's get that far.
The Astrocampus will be here.
Astrocampus will be here. The world around it might be very different, but Astrocampus will definitely be here. All right, well, Emily, while there's a little bit of a lull in proceedings, we'll see whether or not anyone else wanders across with their favourite space question. But in the meantime, today is a big event. There's loads of people. I'm guessing there's probably a couple of hundred. Several hundred
easy.
people have come along today. So what's on offer today? What's happening here at the university to celebrate 10 years of Astrocampus?
Yeah, so we're celebrating a lot of things. We're celebrating, obviously, the thousands and thousands of people who've come to visit us, who have engaged with our school visits, our Cubs Brownie visits, who we've been out to other schools. I think the numbers are pretty astounding when you add them up over the 10 years. It's 70,000 plus
Wow.
people
That's
have
a lot.
engaged with the
That's a lot.
Astrocampus. So we're just really celebrating that.
When you consider also that it's not a stadium venue, right? You're not doing groups of thousands at a time. You're bringing through relatively small groups of school classes or Cubs and Brownies, or even on open days, it's limited numbers of people that can come through at any one time. So tens of thousands, 70,000. That's a lot of work.
Yeah, it's only a small fraction of those people have been able to visit the site, as you say, because we're a limited space site. There's about 5,000 people have been on site, but we've been able to go out into other groups, and we've been really fortunate in that we hosted the Principia Schools Conference. That was with Tim Peake, for example.
Yeah.
And we had hundreds of primary children come to the university. They filled our entire central hall.
That's right. I was there. I was there with my kids. It was awesome.
It was just an amazing event, and they got the opportunity to meet Tim Peake, the astronaut.
Yeah, that's cool. He's visited twice, if I'm not
he has
mistaken.
Actually. Yeah. So 2 conferences.
That's a boost.
It's just been an amazing opportunity. So that kind of engagement lets us extend our reach beyond the kind of 30 people that we can have on the site, but go out to the big groups and talk to them as well. And we've evolved a lot, I think, over time. We've learned how to engage best, what works best with community engagement, what sort of groups work best in enabling people. And we've got a brand new project up and running now where we're using virtual reality to engage with lots of different people, but we're really focusing on as
I'm watching a little girl walking past in the background with her VR goggles on.
Yeah, we got lots of activities. We're focusing on children with disabilities or special educational needs.
Yeah,
engaging them in STEM, which is a sort of maybe something that hasn't been done as much as it should have in the past.
And it does tend to be the sort of thing which, unless an outreach or an educational program is designed with that in mind, it does tend to be the sort of thing which, once you're established, you can take an opportunity to say, well, who are the groups that we're not reaching, and how do we bring them into the fold? And it's great to see. So some of the stuff that we see around us here today, I mean, we've got loads of just sort of broad STEM stuff going on. There's loads of robots. You can probably hear some of the robots clicking away in the background every once in a while. We've got the Cosmodomes, the big inflatable planetarium up the end of the room here. But across the way, we've got some sensory tables where kids can come and sort of get their hands into various materials to sort of feel what the different kind of substances feel like, and how
we've got some kind of 2 setups. So it's on the sensory tables, which I think is really cool.
Yeah.
So we've got the inner rocky planets.
Yeah.
And then we've got the outer gassy planets.
Oh, that's cool.
Yeah.
That's
so the inner rocky planets, they've got water and rocks. So we've got things like kitty litter and water to get your hands dirty, stuck into and play with.
That's nice.
But for the outer planets, we've got ice and shaving foam to represent the gas and the bubbles and the cold.
I thought I saw some kitchen towel over there. I was wondering what that was for, but now I understand.
Messy
The
play's
shaving
always
shaving
great,
foam.
isn't it?
The shaving foam. That's awesome. That's awesome. What else is here today?
So we got our 2 signature Cosmodomes.
Mm-hmm.
So the Cosmodome was actually part of the Astrocampus from its very origins, and that's again one of the so it's an inflatable planetarium, and it's something that we've been able to take out into the community. We've been all around Yorkshire with these domes to
it packs
take
up
them
into
to
the back
school.
of a car, and you can put it in a decent sized classroom. Like they're big without being huge.
Yeah.
They can fit what, sort of a small class?
Yep.
Inside?
Yep, 30 children,
Yeah.
So, I mean, it packs into the back of a Micra, amazingly.
That is pretty cool. Good to know.
Yeah. I've been in with the Cosmodome a couple of times, even out to out Scarborough.
Mm-hmm.
Like sometimes some of these communities that are a little bit harder to reach, they might not have a university in town that can, they can visit, but we can take things out.
Yeah, people who can't come into the Astrocampus themselves, you go to them.
Yeah.
Set it up.
Yeah.
Very cool.
And that's been an incredibly successful program. So much so, we've got 2 now. We had just the 1, we've got 2 now. And we use those for lots of our outreach for the whole School of Physics and Technology, and the School of Physics, Engineering and Technology now. So we do things with our plasma physics. We've got the Sun Dome, which is a version of the Cosmodome. We do things with kind of all different age groups where we're looking at nuclear physics all the way up to plasma. Lots of astro.
It's a great
amazing.
resource, and it's a really interesting atmosphere inside as well in this little dome. So here at the exhibition, there's all of that stuff inflatable planetariums and robots and VR goggles and all sorts of nonsense. But there's also other stuff going on. We've got some talks happening.
So just before this exhibition started, we had our Things That Go Bang, basically,
Right.
talk. It's a,
Lots of science fun for the kids,
yeah,
yes.
it's a really kid-friendly talk all about basically the challenges of going to space, what you have to consider, from everything from how do you get there for propulsion, so hydrogen and bangs, what happens when you get there, and always the most important thing of how do you go to the toilet.
Right, you've got to address that because it is the number one question that everyone wants to know. And something about marshmallows? Marshmallows in space?
So we have a marshmallow person. So
what's that about?
Well, this demonstrates what happens to the human body in a vacuum.
Ah, okay. So the marshmallow playing the role of the human body?
Yes.
Right,
So
and
we pump the vacuum chamber down with the marshmallow person inside, and of course the marshmallow person expands and eventually kind of just goes gooey and mushy. And
that's
everywhere.
very cool. I pity the person who's doing cleanup on this particular demonstration, but yeah, that's pretty awesome. So there's sort of that demo show, and then there's another talk later on?
So we've got Dr. Sarah Casewell coming to us just at the end of the exhibition, and she's going to talk about the exoplanets that she studies, some of these
Where's
really
she from?
From the University of Leicester.
Right, okay.
Yeah, she's an Ernest Rutherford Fellow there, and really excited to hear about her take on the research that she does with these exoplanets, and particularly these really weird brown dwarf exoplanets.
Excellent. So that's a public talk happening sort of
Yeah.
after the exhibition time tonight.
That's right.
And then what? Everyone kicks back with birthday cake and a glass of bubbles or something?
Exactly, yeah.
Perfect.
Yeah, we've done a few things. We've got the Vice Chancellor coming along to have a look. We've got we've got a lovely video that just sort of celebrates some of the activities that the Astrocampus has been doing over the last 10 years.
Is Astrocampus itself going to be open?
We're hoping to.
Because I'm
following
looking
the lecture
outside and I
tonight.
can see blue.
Yeah,
I can see blue sky.
We might even see some stars tonight, so that would be amazing. So after our talk tonight, we're going to open up our telescopes. Fingers crossed that it's nice and clear. That
It's
we can
looking
see some
okay at the
stars.
moment. Yeah, fingers crossed. I mean, earlier this morning it was awful, but
I mean, it's never happened before that we've had a large public event and then had a clear night.
you never know your luck. So, hang on. Before you ask, would you be prepared to ask it into the microphone? So what I'll do is, I'll turn the microphone around and you can speak into it like I am.
I'm Darcy, and are we the only living things in this universe, or have we discovered any signs of life on other planets?
Oh, this is a wonderful question.
Really good question. So it's a follow-on from a question that we had earlier where someone else sitting right where you're sitting right now said, so what do you think? Is there life outside of our solar system? And we had a chat about that. And despite the fact that there are huge numbers of stars in the universe and ridiculous numbers of planets, like there's so many of them, Emily reckons no, and I reckon maybe. But the second part of your question is really, really cool because it's, have we seen any signs of anything that could, like, how do you even look for life? How would we know? Emily, what do you think?
Well, there's lots of places to look for life, right? So we know that there's life on Earth. We can look at other planets in our solar system and even the moons of other planets in our solar system. And that's gotten really exciting. So we did sort of maybe think there might be life on Venus about two years ago, something like that.
Do you know Venus? Do you know where Venus is in the solar system? How do the planet, coming out from the sun, do you know what the planets are? What's the one closest? No, Jupiter's further out. So it's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So Venus is the next one closest to the sun from us, yeah?
Yeah.
And we thought there might have been life there. Turns out no?
Turns out no in this case, but we're looking really, really hard.
Yeah.
And you know that we've got lots of robots on Mars at the moment?
Yeah, I mean, that'd be cool if a robot dug up like a, I don't know, bit of dinosaur or something. That'd be awesome.
Yeah.
That'd be cool.
So it's really hard to get to Mars, and it's really hard to take laboratories to Mars to test all the things that we find. So we've got a rover going around on Mars right now who's taking lots of really interesting samples but burying them. But like a squirrel burying a nut for later, right?
It's burying them?
Yeah.
Why is it burying?
Well,
it's just dug it up.
Well, just leaving them in nice little packages,
Okay.
basically.
What,
But
so for us
saving
to
them
come
for
and pick
later.
up? Oh.
Yeah, with the idea that one day
Yeah.
we're going to have a base on Mars, we're going to have a laboratory on Mars that we can test these things in. Or maybe we'll have better technology and we'll be able to bring them back to Earth. Either way, we can't do those things now, but maybe one day.
Isn't that a cool idea? There's this little rover going around going, well, that looks interesting. quick, bury that under a rock. We'll come back and look for that later. And in a while, we're going to go up there and find all these little packages left by this little rover going around, just leaving his presence all over Mars.
Yeah,
that's really
but that's
cool.
the kind of thing that you could study one day.
Yeah. What do you think? Are you gonna go and study space? You're going to be a Mars explorer? I think you should do that. I have a feeling. I've got a feeling about you. Yeah. What do you reckon? Have you got a question for us? Yeah? Okay. Do you want to ask us your question?
Hi, my name's Eleanor, and I wanted to know, how long does it take for a star to explode?
How long does it take for a star to explode?
Wow.
I hope a really long time, because I don't want to be near it. So
Yeah, so there's two ways you can think about this. The actual explosion is very, very quick, right? So you're thinking about something like a supernova, which is the biggest explosion that a star can do. All of that happens in just a few seconds, right? The big explosion, boom, there it goes.
So
right?
I guess that's a good thing. If you're going to have a really big explosion, get it over like that.
Yeah.
You don't want to hang around.
But it does take a few million years at least for a
Right.
star to get to that point.
You got to wait.
So from when it's born, it will take several million, if not a few tens of millions of years to get to the point where it's going to go boom.
Right. So it's a really long wait, and then it's over like that. So don't blink. Like if you want to see it happen, like don't go to the toilet or anything. Just keep watching that star. Is our sun going to blow up? Is that going
It's
to
not
happen?
going to blow up in a supernova. No, our sun's not big enough. You need to
Right.
be a really big star
Okay.
to blow up like
All
that.
right. All right.
That's a really, really good question.
Really nice question. Thank you very much. Thank you. Enjoy the rest of the show. Thank you. Bye. Hello. You're back. We got you. You've got a question. I knew it. You had this look on your face, which was, yeah, but I'm thinking. All right.
Hi, I'm Lily, and what do you think's like on the other end of a black hole?
Oh, really good question. What's on the other end of a black hole? Because can I just interpret your question here for a second? Like, what I'm imagining you're imagining is black hole is like it's one end of a tube, right? Stuff goes in. So where does it go? What's on the other end of that hole? It's got to be something.
Well, this is a really easy one.
Yeah?
We don't know.
See, that's the trouble with black holes, right? Stuff goes in, but then we can't see it anymore. That's what a black hole is. And if we can't see it, then we don't know what happens to it.
Yeah, so it's possible. If you take all the Einstein's general relativity, all the calculations, all the mathematics we understand about the universe, it is actually possible to have things called wormholes, where you can use black holes or you can use other things to connect bits of the universe that are too far apart to sort of just talk to each other otherwise, but you might be able to connect them through some weird sort of worm loop time string. Absolutely possible mathematically. We haven't seen any.
Does it happen? We don't
But
know.
we don't know.
But
we don't really know how to even test it.
it's allowed.
Yeah.
And that's kind of, there's a whole bunch of science and physics and cosmology, which is about what can we see and what can we learn about the universe from what we see. And we get an enormous way with that. And we can see black holes, despite the fact that they're black, which is kind of weird. But we can't see into them. And then there's this whole other side of physics and cosmology, which is about, okay, so what does the maths tell us? If we do all the equations, what's allowed in this universe? Doesn't mean it does exist, just it might. And wormholes and white holes at the other end of them are allowed. We just have no idea. We've never seen one, which is kind of cool in a weird sort of way. Really nice question. Very nice.
Very well.
Thank you very much. Yeah, you got another one? Okay. Second follow-up question. Here we go.
What about alternate universes?
So do you mean as in like parallel universes? Right. So like the multiverse.
Yeah.
Emily, the multiverse.
So this is actually
We're
comes
going
from,
deep here today.
This is amazing. Yeah,
Whoa.
this comes from the idea of quantum mechanics. So in quantum mechanics, basically the idea is that when particles do things on the very smallest scales, they do things probabilistically. So that means there's a chance that they'll do thing A, but there's also a chance they'll do thing B, right? Everything is chance, effectively. If you extend that idea and make it a bigger take it to the idea of the whole universe. Well, maybe there was a decision. Maybe this star could have formed this way, or it could have formed this way, or maybe planet Earth formed as the third planet, or maybe it formed as the fourth planet. There's different options, right? And those might be, on some scale, governed by probability. So then for every time a decision happens in that probability, maybe another universe happens at the same time where the opposite thing exists. So instead of Earth being the third planet, it's the fourth planet or the fifth or the sixth. And so there's universes where all of those things are true. And you very quickly get to understand there's basically infinite universes, right? Because there's so many different decisions that happen or events that happen. So that's the idea of multiverse. Is it real? This is one of those questions we can never test it. We've got no way of going to another universe and finding out if that exists or not.
But there are a lot of physicists. There are a lot of very, very smart people who really do believe that there's no other way to explain the maths, the mathematics, the theory of quantum physics that we know to be true, because it does so much. All this technology and everything is built from quantum physics. We know it works, but what does it mean? When these possibilities come up where an atom could fall apart this way, or something could happen this way and this way. Lots of people really do believe, no, honestly, at that point the universe really does split. And it splits and it splits and it splits, and you've got this multiverse. But as Emily said, we currently have no way of getting between those universes, so what does that even mean? We don't know. Really interesting idea. It sounds like science fiction, but there's a lot of people who take it very, very seriously. Who knows? Who knows? Good question. Good follow-up question. Thank you. See ya.
See ya.
Bye. Wow. We've gone really deep here today.
Oh,
that's awesome.
They're great, yeah.
That's awesome. We've had black holes. We've had life in the universe from more than one person. We've had white holes and wormholes. Oh, and we've had the multiverse, which is just... I didn't think we were going to go there today. I thought we were going to get a lot of questions about things like comets and meteors. I didn't think we were going to go here. That is really awesome. Well, a bit of time has passed, and we're coming to the end of the exhibition now. And Emily's gone off to set up for the big public talk that's happening a little bit later on. Crowds are thinning out a bit as they head off to the lecture theatre. And that brings us this episode of Syzygy to a close. It's been a fabulous day. So many people wandering around getting into space and STEM and science and all sorts of stuff. It's been an amazing day. So I'm going to sign off in a second. But before I do, just remember, you can always find us online at syzygy.fm. You can find us on Facebook. Just go and search for us there. On some of the social medias, the Instagram, the Threads, that kind of thing. Just go and find us. Tell everyone you know that there's this awesome podcast out there that does great astronomy stuff. Get them on board so that we can grow our audience and help to spread the good word of space. Catch you next time, everybody. Bye.